Okay, so we're going to spend the next three sections of this Exam 1 material talking about number theory. So number theory is the study of the integers, and it's a great topic to talk about for a variety of reasons. Namely, one, we can do proofs with it. It's pretty basic proof, so it's good practice since you guys are kind of at the beginning of learning how to prove things. And number two, it's one of the few topics in mathematics where it's actually fairly easy to get to the fringe and understand some of the unanswered questions. Most areas of mathematics you have to study sometimes for years before you can even understand the unsolved questions in order to do any sort of research on that, but not with number theory. And so what we're going to do is we're going to do just talk about briefly some unanswered questions here. I think I have three big ones, and the first one actually was solved. I used to say recently, but that's not the case anymore because it was actually solved in 1995. So Fermat's last theorem, this should look familiar, right? X squared plus y squared is z squared, right? That's your Pythagorean theorem there for triples. But Fermat's theorem said, well, how about integer solutions when we're talking about x to the n plus y to the n equals z to the n when n's bigger than 2? In other words, are there integer solutions for x cubed plus y cubed equals z cubed, etc.? And Pierre de Fermat had a little thing in the margin of one of his notes where he said he had a little proof for this. And that was that. He never proved it. He just mentioned it. And it actually wasn't solved until 95. It's believed he didn't have a proof for it because if you look at, there's actually an interesting documentary on this. The guy's name is Andrew Wiles. I believe he's out of Princeton, but spent years and years and years working on this problem, and it actually used some kind of a recent interesting area of mathematics that was developed in the 50s, I believe, by a couple of Japanese mathematicians. So the conjecture is he didn't have a proof for it because the proof is fairly involved. If you want to check out that documentary, it's mildly interesting. Anyway, so that one's done, but the other two are not here. So the other one is called the twin prime conjecture. So again, we're going to talk about this later, but briefly, a prime number is a number divisible only by itself in 1, right? We'll revisit this later on, but that's all you need to know for this. So there are many examples of pairs of primes that differ by 2, right? Here's some examples, right? 5 and 7, 11, 13, 7, 19. So the question is, are there an infinite number of these pairs? And the answer is we do not know. That is an open question. Similar sort of an open question is the Goldbach conjecture. It seems possible to write every even number greater than 2 as the sum of 2 primes, right? So here are our numbers, even numbers greater than 2, and notice that we can write them as the sum of 2 primes. Can this always be done? Again, we don't know. It's an unanswered question. Another one, the Greeks were fascinated with what they call perfect integers, and an integer is perfect if it's the sum of its positive divisors other than itself. So 6 is the first perfect number, since its positive divisors are 1, 2, and 3, other than itself, which is 6, and if you add them, you get actually the number 6. So are there an infinite number of these? Again, we don't know. So number theory is certainly intrinsically interesting for its own sake, but you can see you can get to the unanswered questions pretty easy. You can explain these to really a kid in grade school. It's not super complicated. Trying to show these things, however, gets a little more interesting. But so as we always do, we're beginning to talk about a subject. So let's kind of work up to it. We'll do some definitions, and then we'll do some theorems related to that, and then the worksheets will have you proving some of these things. So the first thing we're talking about is A divides B, and we use that line like so. Okay, so we say A divides B when B over A is an integer. Also, B is a multiple of A. If it doesn't divide it, we write it this way with the hash mark through the line. So, for example, 3 divides 6, negative 3 divides 6, 2 does not divide 5, right? 5 over 2 is not an integer. D is what is called the greatest common divisor, or GCD, of two numbers A and B when it's the largest integer, dividing both of them. And then we denote that with the parentheses. So the GCD is denoted with parentheses. Okay, so here we have the divisors of 4. I've actually listed them all out, and the divisors of 2. Notice that the common divisors are listed here, and so the largest one is obviously 2. This is not the way you're going to want to do this. There are some formulas that we'll get to find GCDs a little bit easier, but just to illustrate what we're talking about here. The other thing we're going to talk about, notice that this is denoted with brackets. Okay, so be careful, right? Parentheses is GCD. Brackets is what is called the least common multiple. Okay, so it's the smallest positive integer that's a multiple of both. For example, if we want to look at 4 and 6, here I've listed the first few multiples of each. I've then listed the common multiples, and of course the smallest one is 12. Okay, so let's go through some theorems. The first one is, if A divides B and B divides C, it follows that A divides C. Okay, so how would we prove this, right? Well, again, A divides B means B over A is an integer, and similarly for B dividing C, right? So by definition, B over A is an integer, C over B is an integer. If we take a look at the product of these two, we're certainly going to get an integer, so it follows that A divides C. Okay, and again, just as a little reminder, it used to be QED, but now in textbooks, and so I've adopted that. They just use a little bit of a solid square there to show the end of the proof. Again, if A divides B and A divides C, then A divides linear combination, right? Bx plus cy for all xy integers. Okay. Again, similar sort of proof, right? If A divides B, then B has to equal R times A for some integer R. Okay. And if A divides C, right? So C is a multiple of A. C has to be S times A for some integer S. Notice that I'm using R and S because they don't have to be necessarily the same integer. So take a look at Bx plus Cy, right? We get that from the previous statement, and of course we can factor out the A, and so it follows that A has to divide that combination. Okay. So you can see that the proofs in number theory are neat and clean. We certainly know what this is. We're going to come back to it in the next section because we can use it to find out some other interesting things. The division algorithm. Right, again, this means there exists unique integers Q and R, such that R is between 0 and A, and B is equal to AQ plus R. So we use Q and R, Q for quotient and R for remainder. Okay, so we should all be familiar with the division algorithm. As an example, if A is 7 and B is 592, then the quotient's 84 and the remainder is 4, right? 592 is 84 times 7 plus remainder 4. Notice that 4 is between 0 and 7. Again, I mention this now because we're going to return to it. We're going to use it to find something else out. Here we have theorem 10. So if A and B are positive integers, notice that the GCD times the LCM is actually the product of the two. So again, these are the homework ones that are starred. And the first 5 are pretty much similar to the examples that we've covered in the notes. And then you want to prove these, right, using the similar techniques that we did earlier.